In today's video, we're going to look at polynomials. So we've been looking at these throughout our whole course. We've seen constant functions where f of x is equal to some constant number, y is equal to some constant number. We've seen those. We've seen linear functions where y is equal to mx plus b. That's a linear function. And then in our last video, we looked at quadratics. That's another type of polynomial. A polynomial is just any function. I'm going to call it p of x for polynomial. You could write this as f of x, you can write this as y is equal to this. Completely depends on what you are doing and how you would like to use your notation. But it's any function that can be written in this form. Okay. Each ai, so each one of these a values, is just a constant number, okay? And then n minus 1 all the way down. Each one of those is a non-negative power. So each one of these powers or exponents is non-negative. Okay, that is a big deal with a polynomial. If you have any of those powers, any exponents that are negative, then you do not have a polynomial. So they have to be non-negative integers. And added to that, they do have to be an integer, not just any positive number. They do have to be whole numbers. So each power is non-negative and is an integer. Okay, so you can't have a fraction as a power either. Like I said, we've already looked at things that would be of the form p of x is equal to this type of a function. This would be a quadratic. We've looked at things that would be linear, so a linear function. And we've looked at functions that are constant. Okay, so this is what we've looked at so far. But now we want to extend that to all polynomials. Where we're actually going with this is to actually look at sketching a rough graph for each one of these polynomials. We want to look at the end behavior of the graph. So for any polynomial, we want to see what happens as x goes towards infinity, what happens as x goes towards negative infinity. Use that in order to sketch a graph. Can we find the zeros of the graph? We're going to look at that. How can we look at the particular numbers that solve our polynomial if we set it equal to 0? That's what we're going to look at as we go through all of these different things with polynomials. I want to give you some examples just of things that are polynomials, things that aren't polynomials, just so that we are aware as we go along. First one, let's do p of x is equal to 3x to the 4 plus 4x to the 1/3. This is not a polynomial. If I didn't have this end term here, then I would have a polynomial. I have something of the form constant times x to a non-negative integer power, so that would be fine. But my issue I have is this term at the end here, where I have an exponent that is not an integer. It's non-negative, but it is not an integer. So this whole thing is now not a polynomial because I have at least one term that does not fit our description. So this is not a polynomial. Okay. Something that would look like p of x is equal to 3x to the negative 4 plus 4x cubed. Again, this is not a polynomial. Now we have this term, that exponent, that means that we do not have a polynomial because we have a negative power. So this is not a polynomial either. So every term in your polynomial has to fit the description, otherwise you don't have a polynomial. Okay. Something that is a polynomial is just something that's a constant. if I look at our definition here, I just have a constant value at the end. I don't actually have any x terms in there, but everything fits, okay? I do have a polynomial in this case, so this is a polynomial. Okay. What does the graph of a polynomial look like? Well, we're going to see that it actually depends on the first term, what we are going to call the leading term in our polynomial. But whenever you have a polynomial function, the graph of it must be smooth and continuous. So that's two things that we need to talk about. Graph of a polynomial is smooth and it's continuous. Okay. What do those two things mean? Continuous is an easy one. Continuous means that I can draw the whole graph without lifting my pen from the page. Okay. If at any point I have a jump, I have a discontinuity, anything like we looked at with piecewise functions, I had jumps in my graph. Okay, anything that looks like that is not continuous because when I draw it, I have to take my pen off of the page. So a polynomial will always have a continuous graph. I can draw it as a continuous curve. So this means that you can draw it without lifting your pen from the page. Okay, so there's no jumps and no discontinuities. Okay, so even if there is one point on the graph where it's not defined and then it carries on like normal, that wouldn't be a polynomial because I would have to lift my pen from the page at that point because it would not be defined at that one point. So that would be a discontinuity. Smooth basically means that there are no corners. Okay, you've got no cusps, you've got no corners in your graph. You can draw it as a smooth curve. So there are no cusps and no corners. Okay, so kind of like the definition says, it's a smooth curve. The next thing I want to look at is the degree of a polynomial function. Okay, this is just a definition. When we look at our polynomials, I'm going to quickly write out the form of a polynomial again. Okay, this is a polynomial. The degree of a polynomial is just the number that is the highest power. Okay, so the degree of a polynomial, okay, is just the highest power. So it's n. So that tells me that the degree of a quadratic would be 2. The degree of a linear function would be 1. The degree of a constant function would be 0. Okay. Another thing that I want to look at, which will come up when we actually try to graph these, is leading coefficients and leading terms. The leading coefficient is just the coefficient that is in front of the x with the highest power. So it is this an term here. Okay, it is the constant that is in front of the term that has the highest power in it. So in this case, if you had a quadratic, it would be the coefficient of x squared. Okay, so I'll give you a quick example here. P of x is equal to 3x squared plus 5. Your leading coefficient in this case is the number that is in front of the highest power of x, so the leading coefficient would be 3. The leading term is that whole term that contains that highest power. So it includes the leading coefficient and also x to that highest power. That is the leading term. Okay. So if I take my example here, okay, my leading term would be 3x squared. It's the leading coefficient and x to that highest power. Okay, so it's that whole an x to the n term. I'll do a couple quick examples here where we look at degrees, leading coefficients, leading terms. Okay, I'll do a simple example and then I'll do something that's slightly more complicated that you may come across. I have P of x is equal to 4x cubed plus 5x plus 2. Okay. My degree would be the highest power of x that I have, which in this case is 3. My leading coefficient is the coefficient that's in front of that highest power of x, which would be 4. And my leading term would be the whole term that contains that highest power of x, which would be 4x cubed. Okay. We're actually going to use that leading term to tell us what happens as x goes towards infinity, x goes towards negative infinity, looking at that end behaviour for our graphs when we go through that towards the end of our polynomial chapter. A slightly more difficult example that I want to look at is something of this form. Something that looks like this. I do not want you to multiply all of this out and find out what it is. There is actually a simpler way of doing this. If we're looking at the degree, okay, that is the highest power of x that we could possibly have. When we do this, and if you were to multiply all this out, first thing I want you to look at is what would the power of x be that has the highest degree if I were to multiply all this out? Well, that highest power of x would come from multiplying x squared by itself 5 times. Every other x term, x to the power of something, is going to have a lower power than that, okay? Because we will have multiplied x squared by something of a lower power. So the highest power of x that I can possibly get in this end part here is by multiplying x squared by itself 5 times. So if I do x squared times x squared times x squared times x squared times x squared, I add the powers together and that would be x to the 10. And then that x to the 10 term would multiply this 5x cubed term. And again, you add the powers when you multiply. So that would give me an x to the 13 term. That is the highest power of x that I can possibly get by multiplying all of this out. Everything else would have a lower power of x. So my degree, in this case, would be 13. I get that x to the 10 term, and then I would multiply that by x cubed. That would give me an x to the 13 term. My leading coefficient. Okay, again, you will have to look at this leading term in the second part. Okay, I don't have any other coefficient other than 1 to x squared in that. So when I multiply that x squared term by itself 5 times, I'm going to end up with x to the 10. If I had something other than a coefficient of 1 here, I would have to take that coefficient to the power of 5 as well. But here, 1 to the 5 is just 1. So I've got a coefficient of 1 of my x to the 10 term. So when I multiply that term by 5x cubed, I'm going to get 5x to the 13. Again, if I had another coefficient other than 1 here in front of that x squared, I would have to take that to the power 5 too before I would then multiply by the 5 here, and that would give me my leading coefficient. But right now, I just have a coefficient of 1, multiply it by itself 5 times gives me 1, multiplied by the 5 gives me 5. So my leading term would just be 5x to the 13. So you don't have to multiply the whole thing out, you just have to look at this leading term. What would your leading term be if I took the highest power of x in my parentheses, took it to that power, and then multiplied it by what's outside the parentheses? Now I want to start looking at that leading term. Okay. The leading term can also be called something called a power function. So if you see the words leading term or power function, we're actually looking at the same thing here. It is that term that contains that highest power of x. What that tells us is how this whole polynomial is going to act as x gets incredibly large. Okay, let's look at this polynomial that I have up here. Okay, as x gets incredibly large, it goes towards infinity, positive infinity. Okay, if I cube that incredibly large number and then multiply it by 4, so if I take this term here, that's going to go up and up and up and up much faster than just multiplying that number by 5. Okay. So by cubing that number and then multiplying it by that coefficient of 4, I'm going to get very large very quickly in comparison to just multiplying it by 5 or just taking a constant. So you see that as x gets very, very large, that leading term is the term that's going to get largest the fastest. It's the one that dominates your whole polynomial as x goes towards infinity or as x goes towards negative infinity. It's the one that gets largest the fastest and the one that's going to dominate all the other terms. So this leading term, this power function, just gives us an idea of the overall shape of the graph and tells us what happens at the ends as x goes towards infinity and x goes towards negative infinity. The problem that you have is if it's not in this standard form that we've been looking at of an x to the n all the way down to a0. Sometimes you may end up with a polynomial that could be in this form, where it has been factored. Not the end of the world, but you may have just all these parentheses multiplied together. So this polynomial is not in standard form, it has in fact been factored. So to find that leading term, to find that power function, to find out what would happen as x goes towards positive and negative infinity, you would multiply it all out and you would see what your leading term was, and then you would use that to say, okay, as x goes towards infinity, this is what happens overall because that leading term is the one that's going to dominate and get very large very fast. But what we can actually do, just like I did in my second example here, is we can just look at what our leading term would be by taking each parenthesis, looking at what our leading term is in that parenthesis, and then multiplying all of those leading terms from each one together, and that would give us the leading term of the overall polynomial. So here, if I were to find for my first parenthesis what the leading term of that one would be, well, it would be a1 x to the c1. Okay, that is the term that is going to have the largest power of x when I multiply this all out. Okay, everything else is going to have a lower power of x by multiplying out that particular set of parentheses. Looking at the next one, I would have a 2x to the power c2, and you would multiply all those leading terms together to give me the leading term of the overall polynomial. Okay, that would be the highest power of x that I could possibly get by multiplying out this whole polynomial. You can simplify this and say that you would have all the constants multiplied together at the front, and this is what you would get. You would take each one of the constants to that power, and then x to the c1 times x to the c2 down to x to the cn. If you multiply that variable x by different powers, you would just add the powers, so you would get a1 c1, a2 c2, an cn, x to the c1 plus down to cn. Okay, so that would be our leading term of the whole polynomial. What I want to do is give you a quick example. I'm just going to do one in standard form first, and then we can go ahead and look at one that has a slightly different setup. The first one that I want to do would be polynomial negative 2x to the 6 plus 3x squared plus 1. Okay. What's my leading term in this case? Well, my leading term is going to tell me what happens as x gets very large, both positively and negatively. My leading term is negative 2x to the 6. Okay. Now I'm going to use that to tell me what happens as x gets very large in the positive direction and x gets very large in the negative direction. Whenever you do this, big key here is to look at the power. Okay. You want to look at whether it's odd or even. If that power is even, it's going to look very much like a quadratic graph. Okay, remember, quadratic graph, we've got x to the power 2 as our leading term. But all polynomials where their leading term is even are going to model that same kind of behavior. It's going to look slightly different, but towards the ends, you're going to find in some way it will look like that if that leading term of x has an even power. If it has an odd power, it's going to act very much like an x cubed graph. Now remember, an x cubed graph went like this. Okay, so even though they're not going to look exactly like the x squared and the x cubed graphs, for odd and even powers of leading terms, they will look roughly like this when your leading term is even power, leading term is odd power. The only thing that we do have to be careful with, and this happens in this case, is we have a negative for our coefficient. So of course that is actually going to flip our graph in that x-axis. So we're actually going to end up with a graph that models that kind of behavior. Okay, so just be careful with that. If you do end up with a negative coefficient, it is going to flip that graph in the x-axis, and you may end up with the opposite from flipping it in that x-axis. But it will give us the rough behavior of what happens as x goes towards positive and negative infinity, and that's really what I'm looking for here. So my leading term is negative 2x to the 6. Now, if I had a positive 2 times x to the 6, as x went towards infinity, so as x goes towards infinity, my whole equation, my y, my p of x, goes towards infinity. As x goes towards negative infinity, I also go off to infinity in that y direction. Okay, so my whole term would go off towards infinity. In this case, I have a negative 2 times x to the 6. I've got a negative, so I'm dealing with this flipped graph here. As x goes towards infinity, I now find that my polynomial is going to go towards negative infinity. And again, as x goes towards negative infinity, I'm also going to have my polynomial go towards negative infinity. So for this case here, because my leading term, this tells me what happens as x goes towards infinity, as that is the term that grows largest the fastest, we find that as x goes towards infinity, my whole polynomial, p of x, is going to go towards negative infinity. And as x goes towards negative infinity, p of x is also going to go towards negative infinity, okay? So you may find that there will be some type of thing where it will jostle around in the middle. So instead of just a smooth graph, you may find that after all your transformations, etc., your graph may end up looking something like this, okay? But your end behavior, what happens as x goes towards positive and negative infinity, will always model something like that x squared graph if you have an even power for your leading term. If you have an odd power for your leading term, it's always going to model something that looks like that x cubed graph. It may jostle around in the middle again, but it will model something like that x cubed graph. And just be careful, you do have to flip it if your leading term has a negative coefficient. Okay, and the last example I want to look at will be p of x is equal to 5 x minus 3 to the 7, 2x plus 4 to the 3, x plus 1. Okay. I want to see what happens at the ends as x goes towards infinity, x goes towards a negative infinity. So first thing I need to do is to actually find that leading term, to find that power function. So what I'm going to do is I'm going to see what my leading term would be by multiplying out the leading term for each one of my parentheses. So for this parenthesis here, I can see that my leading term would be x to the 7. My leading term here, well, I've got 2x, which would be multiplied by itself 3 times, so it would be 2x cubed. And then I've just got an x on the end, so my leading term here is x. It's to the power 1, so x to the 1 is just x. So if I then multiply everything together, I've still got that 5 on the outside, and then I've got x to the 7, I've got 2x cubed, and I've got x. If I multiply all of that out, multiply it together, I'm going to get 2 cubed here will give me 8, and then 8 multiplied by 5 gives me 40. Then I've got x to the 7, x cubed times x. So my leading term here would be 40x to the 11 for my polynomial. So here we have an odd power. So that tells me that it's going to act in a very similar way to x cubed. So if we think about the graph for x cubed, okay, we have a positive coefficient for our leading term here. So our leading coefficient is positive, which means I don't have to flip anything in the x-axis, and it's going to act very similarly to our x cubed graph. So as x goes towards infinity, my polynomial will go towards infinity, and as x goes towards negative infinity, our polynomial will go towards negative infinity. Okay. So we see here we had our degree 11 polynomial for our leading term for our power function, and then we compared it as it was an odd degree. We compared it to what would happen with that x cubed graph because it would work in a very similar way as it has an odd power. We checked our leading coefficient to make sure if it was positive or negative to see if we had to flip that graph, and then that showed us exactly what happens at the ends of this function as x goes to infinity and x goes to negative infinity.